Good morning to one and all. In today's lecture, we will discuss about the demodulation of FM wave using PLL, that is phase lock loop. So PLL is basically the widely used method for the demodulation in FM wave because of its low cost and superior performance, especially when the SNR is low. PLL is a closed loop feedback system. PLL is used as indirect frequency demodulation and carrier synchronization. PLL basically consists of a voltage controlled oscillator, a multiplier, and a loop filter, that is low pass kind. So the function of VCO, that is voltage controlled oscillator, is to perform the frequency modulation on its own signal, that is called as control signal. Here, the multiplier is used for the multiplication of the incoming signal FM by the output of VCO. The work of loop filter is to remove the high frequency component contained in multiplier outputs. So we will discuss it with the help of a block diagram. Here we have an incoming signal FM wave ST that is multiplied by a VCO that is represented as RT and produces an output that is error signal ET. Here the loop filter contains we will at the output of error signal we will get both the high frequency component as well as low frequency component, but the loop filter is a low pass kind, so it will pass only low frequency component and neglect the high frequency component and produces an output that is VT. Now here we assume that if a VCO is adjusted such that when the input, that is control signal Vt, is equals to 0, then it must satisfy two conditions. First, the free running frequency of VCO is set to certain frequency Fc. Second, VCO output RT has a 90-degree phase shift with respect to unmodulated frequency Fc. We know the incoming FM wave is given as St is equals to AC sine 2 pi Fct plus 2 pi Kf integrate m tau d tau. So your 2 pi Kf integrate m tau d tau is equals to phi 1 t. That is incoming FM wave angle. So your St is equals to AC sine 2 pi Fct plus phi 1 t. Here your AC is your carrier amplitude and Kf is equals to frequency sensitivity of frequency modulator responsible for generation of SC. Now we'll define the locally generated FM wave by VCO is given as RT is equals to AV cos 2 pi Fct plus phi 2 t, where your phi 2 t is equals to 2 pi kV integrate V tau d tau. Here your V tau is the controlled voltage. AV is simply your amplitude and kV is the frequency sensitivity factor of VCO. Now if we multiply our incoming signal FM wave ST by the locally generated FM wave RT, it produces two components. So our error signal ET will be equals to AC sine 2 pi Fct plus phi 1 t into AV cos 2 pi Fct plus phi 2 t. So the first term represents your incoming FM wave and the second term represents your locally generated FM wave. Here we note a point. The function of the feedback loop around the VCO is to adjust the angle phi 2 t equals to phi 1 t. Now using the trigonometric identity, sin A cos B is equals to half sin A minus B plus sin A plus V. So we can say our error signal ET will be equals to AC AV by 2 sin phi 1 t minus phi 2 t plus sin 4 pi Fct plus phi 1 t plus phi 2 t. Now here we introduce a multiplier again that is given by Km. Km is equals to 1 by 2. So in error signal in place of 1 by 2 we put Km. So error signal ET is equals to kmacav sine phi 1t minus phi 2t plus kmacav sine 4 pi ct plus phi 1t plus phi 2t. Now the first term is your low frequency component, that is the difference between the frequency term, and the second term is a high frequency component, that is double frequency term 4 pi fct. So we know our loop filter is a low pass filter, so it will neglect the high frequency component and it will pass your low frequency component. So ET will be equals to kmacav sine phi ET. So your phi ET is basically equals to your phi 1t minus phi 2t, that is phase error. So in place of phi 2t, if we put 2 pi kV integrate v tau d tau, so phi ET is equals to phi 1t minus 2 pi kV integrate v tau d tau. Now in error signal we have a condition. First condition, when phi ET is equals to 0, the PLL is said to be in phase lock. Second, when your phi ET is less than 1, then the PLL is said to be near phase lock. So we use the approximation. If your sin phi ET is nearly equals to phi ET, that is accurate within 4% only. So your phi ET is less than 0.5 radian. So we can say the error signal is equals to kmacav phi ET. In place of sin phi ET, we put phi ET. Now here we introduced a new parameter, that is K0. K0 is equals to Km kV AC into AV. So in place of Km AC AV, we put K0 upon kV. So our error signal ET is equals to K0 upon kV phi ET. Now if we say if our loop filter consists of an LTI system having an impulse response ht in time domain, then what will be the output at Vt? Now we consider that let ht is an impulse response of any loop filter. So the output at Vt will be equals to Et convolution ht, that is the output of LTI system. We know the output of any LTI system is given by the convolution of incoming signal and impulse response. So output Vt is equals to integrate minus infinity to infinity e tau ht minus tau d tau. Now this equation constitutes a linearized feedback model of PLL. So what we did, we basically did that we see that error signal have two conditions. First, when your phi ET is equals to 0, then PLL is said to be phase lock. Second, when your phi ET is less than 1 radian, then the PLL is said to be near phase lock. So we may use the approximation then that sin phi ET is nearly equals to phi ET. So error signal ET is nearly equals to Km AC AV phi ET. Here we introduced a new parameter, that is K0 equals to Km kV AC AV. So in place of Km AC AV, we put K0 upon kV. So our error signal ET is equals to K0 upon kV phi ET. Now we consider that our loop filter consists of an any LTI system having an impulse response ht. So if Vt is equals to Et convolution ht, we know output of any LTI system is given by the convolution of incoming signal and impulse response. So we can say over here that the output at Vt will be equals to minus infinity to infinity e tau ht minus tau d tau. So this is all about PLL. In the next lecture, we will discuss the next unit, that is unit 4. Thank you.